All right, please let me know if the audio and video are working properly. Good morning to you all, and as you can see, today we are going to talk about some special cases while constructing Routh table. And of course, I believe you remember what we discussed in the last class, and there we discussed how to construct the Routh table. And using Routh table, we were able to find out how many poles a system has in the left half plane, how many poles a system has in the right half plane, and how many are on the geometric axis. Uh, we haven't yet, talked about how many poles are on the geometric axis, but we are going to talk about that today. But the idea was that without actually solving the equation, we were able to find out whether a system was stable or not using the Routh-Hurwitz criteria, right? And it was split into two criterion. And for example, the first one was the necessary criterion, and the second one was the sufficient criterion. And based on these two, we could determine whether or not a system is absolutely stable. Okay. So today we're going to look at a few edge cases. Edge cases are special cases, right? So special cases, and we then are going to incorporate those ideas and figure out what those special cases mean. And then we are going to actually use our overall ideas, all of it, the total concept, all of it into discussing conditional stability. Okay, so sometimes what happens is that a system is conditionally stable sometimes, unstable sometimes. Okay, so we would be able to actually figure that out as well. So that is something we are going to do. All right, just hold on. All right, so let's talk about the edge cases that we sometimes encounter in while actually doing this Routh-Hurwitz problem here. Okay, constructing the Routh-Hurwitz table. All right, so let's do that. So let's take a simple example. Let's say I have a transfer function that has some numerator polynomial, I don't care, and in the denominator it has something like right. So let's say we have a situation like that. All right. So we know, of course, we are trying to find out the pole locations, not exactly the pole locations, but trying to figure out how many poles are on the left half plane, how many poles are on the right half plane, right? At least that is something we are going to figure out. So we are constructing the Routh table because we see that it satisfies the necessary condition. So this polynomial, the denominator's polynomial, satisfies the necessary condition, right? So not a problem. So all of the coefficients are present. So the coefficients are 1, 2, 10, 20, and 5. So all of the coefficients are present, and all of them have other signs, like all of them are positive, right? So there is no combination of negative, positive, and none of them are 0. So no coefficients are missing here. Okay. So it satisfies the necessary condition, so not a problem. So we can say happily that the necessary condition has been satisfied. So this is now a candidate that can be checked for the sufficient condition, right? So necessary condition is satisfied. So this could be a polynomial that has all of its poles, the roots in the left half plane, right? This polynomial could be a Hurwitz polynomial. We're not entirely sure. We have to check for the sufficient condition. So that is exactly what we are going to do. But right now, since it satisfies the necessary condition, we know that this is a potential candidate for being a Hurwitz polynomial, right? So the denominator's polynomial must be a Hurwitz polynomial for a system to be stable. That is something we already know. All right. So again, just hold on. All right. So now let's take this polynomial and let's construct the Routh table. So because we are checking the sufficient condition. All right. So let's construct the Routh table, and of course we are going to start from s to the power 4 row here. So that's going to be s to the power 4, and then we have the s cube row. Let's construct these two first. All right. So of course we have 1 here, that's the coefficient. All right. So we have 1. So first 1, then 10, then 5. So 1, 10, 5, and then we have 2, 20. So 2, 20, and since there is nothing here, we can assume it to be a 0. All right. So let's get rid of this. You already know how to construct the first 2 rows at least of the Routh table. Now let's construct the next few rows of the Routh table. But before we actually proceed, you might remember that we can actually do some reduction on this Routh, on any of the rows. What we could do, we could factor out any positive factor, okay, to simplify our calculation. I told you that it does not change the final results in any way. It does not change the final conclusion in any way. Okay, but you can take positive factors out of any row in the Routh table to simplify your calculation. It does not change the outcome. Okay, it does not change your inference. Okay, what decision you are going to come up with, or what inference you are going to end up with, that does not change at all. Okay, so it would still indicate the exact same result if you hadn't taken the factors out. So what happens is that we can see that in this row we have 2 and 20 and 0, of course. So we can take a positive factor of 2 out of this. So that can be done. So what we can do, so this is the correct way of doing this. So what you do when you are, of course, writing in a paper, what you would do, you would say that instead of constructing that previous row, what we have done, we have constructed a new row for s cube. So that is a discarded row. And for the new row, I write 1, 10, and 0. Instead of just crossing them and writing 1, 10 here, okay, because that's a very bad thing to write. Okay, so we would say this is a discarded one. Okay, we are going to discard this row. Okay, discard this row, and instead we would construct a new row that actually would tell us give us the same information later on. All right, so this row has been discarded. All right, so that is something you can do. So this s cube row has been discarded, and instead we have this s cube row. Okay, not a problem, right? Because we have taken a positive factor out, so we can take any positive factor out, but we can actually opt to not do that as well. Okay, you could just skip 2 and 20, you would end up with exactly the same inference that you would draw otherwise. All right, so let's now remember that this is the pivot term, and we then have to calculate this product and subtract this product from it and divide it by the pivot term to construct the element here. All right, so that is something we have to do. So 10 minus 10 divided by 1. All right, so this becomes 1 times 10 minus 1 times 10 divided by 1. So that's a 0, right? That's a 0. See, I'm not writing these calculations anymore because I believe by now you understand how to do these calculations. So that's a 0 here. What we get is a 0. All right, nice. And then we have to do this calculation. 1 times 5, so this product minus this product divided by this. So this now becomes 1 times 5 minus 1 times 0, that's 5 divided by 1. So that is 5, right? That is 5. All right, now we have a situation. What kind of situation is that? When I now try to construct the s to the power 1 row, I have a problem. What is the problem? That of course the next pivot term is going to be this one, right? The next pivot term is going to be this one, and unfortunately this is a 0. And what is the problem there? The problem is that the next calculation then boils down to this: 0 times 10 minus 1 times 5. So this times this minus this times this. Okay, 0 times 10 minus 1 times 5 divided by 0, because we have to divide by the pivot term. That's how we construct the next element in the Routh table. Unfortunately, divide by 0 is not defined, right? It's not defined. So this is something we cannot calculate anymore. This is something we cannot calculate anymore. This is called difficulty 1. So this is one of the edge cases. This is one of those cases that might arise that does not conform to standard results. Okay, So this is known as the difficulty 1 situation while constructing the Routh table. So let me just write that down. Okay. So what we are discussing is difficulty 1, known as difficulty 1 situation while constructing the Routh table. So in Routh table, when you are constructing the Routh table, you might find this difficulty, that the pivot element in a row becomes 0, and that way it becomes impossible for us to actually continue the calculation from that point onward, right? So it becomes very difficult for us to continue the calculation from that point onward. And there are two ways. There are two ways in which you can handle this problem. Okay, there are two ways in which you can handle this problem. One of the ways is to actually construct something called a reciprocal polynomial. Okay, reciprocal polynomial. I'm just giving you the name. I'm not going to explain that particular scenario. But what you do, you take this polynomial and you understand the fact that you are trying to solve this polynomial, s to the power 4 plus 2s cube plus 10s square plus 20s plus 5 equal to 0. What you instead do, you solve for the reciprocal variable. So what you do, you replace s with some other variable that's the reciprocal of that. So let's say p. So it becomes 1 by p to the power 4 plus 2 by p cube plus 10 by p square plus 2 by p plus 5 equal to 0. Okay, the idea is very simple. Let me just so this is what you do, but this is not the thing we would do. Okay, this is one of the ways in which you can solve this problem, just to inform you about this. All right, so that's plus 5 equal to 0. So what you are saying, you are assuming that p is nothing but 1 by s, or in other words, s is equal to 1 by p. Okay, now of course let's simplify this. I mean, let's multiply this with p to the power 4, because we know that p equal to 0 is not a solution, because s equal to 0 is also not a solution. S equal to infinity is not a solution, right? So that's obvious. And from that, what we get is that this equation becomes 1 plus 2s, sorry, 1 plus 2 p plus 10 p square plus 20 p cube plus 5 p to the power 4 equal to 0. So in reverse order, if we write it in the proper order, it becomes 5 p to the power 4 plus 20 p cube plus 10 p square plus 2p plus 1 equal to 0. So this becomes the polynomial what you are trying to solve for, right? So this becomes the polynomial. Now obviously what you have to do now, you have to construct the Routh table accordingly. We have to construct the Routh table, and from that you can bring out the same inference, because the thing is, if a certain pole, okay, a certain solution lies in the left half plane. So if s is something like, if s, the idea is that if the real part of s is negative, then also the real part of 1 by s is negative. Okay, so the idea would be very similar. So idea is that if one of them has negative real part, the other one would also have negative real part. So the sign changes would still indicate how many poles are there in the right half plane. And this time around, that situation of that having a 0 in one of the pivot elements would now be removed. Okay, so this is one of the ways in which actually you solve this problem. Say you do the same calculation for this reciprocal variable and you calculate the same thing. So this is one of the ways in which you can solve this. So this is one of the ways. Assume p as 1 by s and construct the Routh table. Now construct the Routh table, I am saying now. All right. All right. So now you can construct the Routh table, and that would actually solve the problem. Okay. That difficulty situation will not be there anymore. Okay. But this is not what I rather like to do. Okay. And in fact, this is not the recommended way of doing it, because that actually allows you to discard everything that you have calculated so far. Because see, if you do this kind of calculation, what happens is that whatever you have done so far gets discarded. Maybe so you are, maybe imagine you are doing this for a 10th order polynomial, right? In that case, you might have received this 0 element in one of the columns, one of the pivot elements, 0 value in one of the pivot elements in maybe s to the power 2 row. So that far you have already constructed 8 rows, right? And then if you have to do this sort of calculation, reverse the polynomial, okay, calculate the reciprocal polynomial, for example, and do the same calculation back again, then you actually are discarding the entire route table that you have constructed so far, right? So if I follow this route, we have to actually discard this entire route table, whatever we have constructed so far, and we have to start from scratch. Now this will be a route table on P, okay? But the same thing, exactly the same thing will happen, and the number of sign changes would indicate the number of poles in the right half plane of the system, and such, right? Now here we are going to actually tackle this with another way, right? So we are going to discard this row instead. So instead of actually discarding this entire route table, we are going to discard this row as once again. So we are going to discard this. Okay. We're going to discard this row, and we're going to reconstruct that s to the power 2 row. Okay. And while we reconstruct this s to the power 2 rows, this is how we actually tackle this problem. This is one of the ways, and this is how we actually tackle the problem. At least I tackle the problem whenever I am faced with this. So the thing is, we assume something like an epsilon, and the remaining 5 is there. Now what is this epsilon? This epsilon is a very small positive quantity. So instead of having a 0 here, what we say is that we, instead of having 0, we have a very small positive quantity. So this epsilon is a very small positive quantity. So it's a positive quantity, but really small. Okay, so epsilon is a very small positive quantity. So that is what we replace that with. So this is one of the ways in which you tackle the difficulty 1 situation. So this is one of the edge cases in constructing the route table. All right, so we have discarded this row now. All right, so I believe you understand what we are doing here. Now this is the pivot element. Now this is the pivot element, so we have to do this multiplication, subtract this product, and divide by epsilon. So now let's write this down. So this becomes 10 epsilon minus 5 divided by epsilon. So there is no simplification that we can do on this. 10 epsilon minus 5 divided by epsilon. So that is what the calculation becomes here. All right, and of course here we have a 0, but we don't have to put that because we can skip writing that. And then we have the s to the power 0 row, and there of course we have a 0 here. We have to assume that. So multiply this with this, subtract this product, and divide by this. All right, so we have to do this product. We have to calculate this product and subtract this product and divide by this. So we are going to actually have this times 5 minus 0 divided by this. So that is going to be just 5, right? So now we have successfully constructed the route table here. Okay, we have successfully constructed the route table. We can discard these rows. The discarded rows are not going to be considered, right? Now let's look at the sign changes. Okay, so now we have a positive to positive change. No, so not a problem. Positive to positive. So now we have a positive to another positive, because epsilon is a positive quantity. Okay, not a problem. So positive to positive, again positive to positive. Now what about this quantity? Is it a positive quantity or negative quantity? So this one I'm talking about. Is it a positive quantity or a negative quantity? The thing is, you have to understand that epsilon is a very small positive quantity. So if epsilon is a very small positive quantity, then 10 epsilon is also a very small positive quantity. All right, it's a positive quantity, but it's a very small positive quantity. So now this very small positive quantity, when I subtract 5 from that, it becomes a negative quantity, because this is a very small quantity, right? Very small positive quantity. So when I subtract 5 from that, the numerator actually becomes negative. The denominator is still positive, okay, because it's a positive quantity nonetheless. So this whole thing is actually a negative quantity, right? Because this is a very small number, and then we are subtracting a negative, subtracting a number from that. So from that we see that since this is a very small number, subtracting 5 from that makes it a negative number, okay, and dividing it by epsilon, which is a positive number, keeps it a negative number. So this is a negative number, so we have a positive to negative transition, okay. So this is a negative number, so we have a positive to negative transition. So this is a sign change, okay. This number is a negative number. What we have obtained here is a negative number, okay. So this is a negative number, and then 5 is a positive number, so we actually have another sign change. So 5 is a positive number, so we have another sign change. So these are the two sign changes we see, okay. So one from positive to negative, and one from negative to positive. So just like that, as usual, it does not satisfy. So there, since there are sign changes in the first column of the Routh table, it does not satisfy the sufficient condition, and we now know about the pole locations, right? So we now know that there are, since there are two sign changes, so we are writing since there are two sign changes in the first column of the Routh table, there will be two poles on the right half plane, and the remaining, how many poles? Of course, the system had 4 poles. It's a fourth order system, okay. It's a fourth order system, so it had 4 poles. So the remaining, how many? 4 minus 2. We already know where the 2 are, right? We know that the 2 poles are on the right half plane, so remaining 2 are, rather will be, on the left half plane. So in any case, we know that since at least having even one pole in the right half plane makes the system unstable. Now we have 2 poles in the right half plane, definitely the system is unstable. So unstable system. This implies that the system is unstable. The system is unstable. Okay, all right. So please tell me if you have any confusion regarding what we discussed here. So this is the sign change indicating positive to negative. This is also a sign change indicating negative to positive. All right, so please tell me if you have any confusion regarding what we are discussing right now. So this is difficulty 1 situation that we might have. So these are 2. So we are going to again now talk about difficulty number 2. So these are kind of type of edge cases that we might encounter. Okay. All right, so far I think it's easy to understand, right? So now let's talk about another difficulty, which is known as the difficulty type 2. Difficulty type 2. So there might be another type of difficulty, and for that I have curated problems so to actually showcase this sort of things, okay, because of course I have to showcase this sort of things, right? So let me just write. All right, so that's the denominator's polynomial, and of course we have something in the numerator, and say this is my transfer function. All right. So that's a denominator's polynomial. So not a problem, I hope. Okay. So now let's construct the Routh table. Of course, this satisfies the necessary condition. So we are choosing things that satisfy the necessary condition, because if it does not satisfy the necessary condition, there is no question of constructing the Routh table, is it? Is there? Because see, if it does not satisfy the necessary condition, then we know it's an unstable system. We don't deal with unstable systems. We don't want them. So this is satisfying the necessary condition nonetheless. Okay, the necessary condition has been satisfied. So not a problem in that regard. Okay. So now let's talk about how we construct the Routh table once again. Let's construct the Routh table. Okay, just one thing. Yeah. All right. So when we construct the Routh table, now it's gonna start from x to the power 5. So it's gonna be x to the power 5, x to the power 4. These two are going to be the rows. So now, of course, we have 1 here. So the first coefficients is going to be 1, 8, 7. So is it 1, 8, 7, right? It's going to be 1, 8, and 7. Let me just make sure I have done it correctly. All right, and the next ones would be 4, 8, 4. Now, of course, you might want to reduce this fourth row, okay, s to the power 4 row here, because we see there is a positive factor that can be taken out of this, so to make the calculation simpler. Okay, that is exactly what we do. So what we do, we discard this row. Okay, we discard this row because we now put a simplified version instead. Okay, so we are discarding this row. Instead, what we are doing, we are putting a simplified version instead. So s to the power 4 row now becomes 1, 2, 1. So we have taken out a factor, positive factor of 4. Okay, so we can only take positive factors out. Okay, so we're saying taking positive factor out. So that is something we can actually do. Right? All right. So these two are the first two rows, s to the power 5 row and s to the power 4 row. So we have those. So this is now the pivot element. We do this product and then subtract this product and divide by the pivot element. Okay, so we construct the s cube row. All right, not a problem. So what we have is that we have 8. All right, 8 minus 2 divided by 1. So that's going to be 6. Okay, not a problem. So now this times this minus this divided by this. Okay, so it's going to be 1 times 7 minus 1 times 1 divided by 1. Okay, you discard this row completely. So we have 7 minus 1 by 1. So that's once again 6. Now the moment we have something like this, we can actually once again take out the factor and discard this row. So let's discard this row. Okay, you might see that in some books people just cross this out and write 1 1 instead. You can do the same thing here. Okay, for the sake of simplicity, you can do that, but you should ideally discard this row and write a new one. Okay, ideally you should discard this row. So that's a discarded one once again. And instead now we have all right, so we can actually discard this, and of course we write the simplified one. So s cube row now becomes 1 1. Again, this is completely discarded. Okay, this is completely discarded. This is discarded. This is discarded. You see. Okay, these three are there currently. All right. So that's the idea here. You can always write something like this, but this is not recommended. But you can always do something like that. Just keep in mind. All right, so I could write a 0 here, of course, because I would actually need it. But you understand, if nothing is there, it is assumed to be a 0. All right, so now construct the s square row there. Now, when we construct the s square row, you see that we have 2 minus 1. Okay, so 2 minus 1, so that's 1. Okay, all right, not a problem. And then we have, did I make any calculation or mistake? Just hold on for a second. So it was 8, 6. Okay, no problem. All right, so that's 1. And now we have this times this minus this times whatever 0 here. So that's going to be just 1. All right. So now let's construct s to the power 1 row. That obviously becomes 0 here. Okay. That obviously becomes 0 here, right? So now this is something we are assuming to be a difficulty 2 situation, because, okay, I cannot, unfortunately, this is quite unfortunate. I cannot tell you what I wanted to tell you. You know what? Let me construct a better example maybe. Okay, so we are going to actually have a better example shortly, so don't worry. Okay, right now what you see is that we have a row that has again 0. So there are 2 ways in which you can handle this problem. So you can actually consider this to be an epsilon. Okay, it's to be an epsilon, and once again you can assume it to be a difficulty 1 situation, right? Difficulty 1 situation, and handle it that way, right? Now there is another way in which you can handle this sort of problem. You see, there is a very distinct scenario, distinct problem here. In the previous one, you saw that the first element of the row became a 0. So the distinction here. You saw that the first element of the row became a 0, and the next element was there. It was a non-zero element, right? It was a non-zero element. So that was difficulty 1. So in difficulty 1, what happens is that the first element becomes 0. So only the pivot term becomes a 0, and the remaining terms remain without any problem, right? Some of them might be 0, but some of them do remain. But now here in this s to the power 1 row, we just have 1 element. Okay, if I assume another element to be present here, which I can, that has to be 0. So what I instead have, we have a row of zeros. So previously we had a pivot element that was 0. Okay, in the difficulty 1 situation, we had a pivot element that was 0. So this is giving us the difficulty 1. So pivot element, so 0 pivot element, I mean. So that's called difficulty 1. Okay, so that's 0 pivot element, and that's the difficulty 1 situation, right? Now here we have another problem where we not only have a 0 pivot element, but we have a row that is completed with zeros only. Okay, that is filled with zeros only. So this is a row that has zeros only. So this is not just a pivot element that is 0, but this is a row that has pivot all elements equal to 0, right? So this is row of zeros. This is known as difficulty 2. Okay, not just a pivot element is 0, but the entire row is made up of zeros. Now this sort of problem, this sort of situation, we are going to solve another problem like this, so don't worry. This sort of situation that we might encounter is known as the difficulty 2 situation, and this actually gives us a divisibility problem. Okay, once again the problem would be to actually use this as a pivot term and calculate the next term, but this actually gives us a divisibility problem. What happens is that the corresponding polynomial, the idea is that when this happens, when an entire row becomes 0 in the Routh table, the previous row, so in this case this one, the s square row, gives us something called the auxiliary polynomial. Okay, this row gives us the auxiliary polynomial. So what is the auxiliary polynomial? What is the auxiliary polynomial? The auxiliary polynomial is the corresponding polynomial. Just go back. So I wrote a 1 here, 8 here, 7 here. It indicated that I actually had, so this was the s to the power 5 row. So this was 1 s to the power 5, 8 s cube, 7 s to the power 1. Exactly, right? So 1 s to the power 5, 8 s cube, 7 s to the power 1. Okay, so that's how the polynomial coefficients are, right? So again, this is constructed through polynomial divisibility and things like that. So next one, in the s to the power 4 row, I have 4 s to the power 4, 8 s square, 4 s to the power 0, and that is exactly what it is. So 4 s to the power 4, 8 s square, 4 s to the power 0, right? So these are the things we have. So in any row, if I am actually thinking about the corresponding polynomial, these can be once again very easily constructed because every other element gets every other power. Okay, decreased by 2. So for example, take this one. Okay, take this one maybe. Okay, so what we are talking about? We are talking about 6s cube, 6s to the power 1. That's the polynomial actually. So we just write the coefficients of the polynomials, but the other things are assumed here. So this s square row, I told you that this becomes the auxiliary polynomial. So when we have an entire row of zeros, then the previous row becomes an auxiliary polynomial row. And the auxiliary polynomial correspondingly is 1 s square plus 1 s to the power 0. So the auxiliary polynomial is simply s square plus 1. Now the thing is, the Routh table or the entire construction tells us that whenever we encounter an auxiliary polynomial, what is an auxiliary polynomial? The auxiliary polynomial is constructed, a polynomial that is constructed by just the previous row when an entire row becomes 0. So this entire row became 0, the previous row becomes an auxiliary row. Okay, so this entire row became 0. So entire row became 0. So the previous row becomes an auxiliary row. Okay, so entire row became 0. So the previous row becomes an auxiliary row. Okay, becomes an auxiliary row. Now, what is this auxiliary polynomial? What is this auxiliary row? The point is, it's really interesting. So this polynomial that we have obtained, okay, so this s square, so s square plus 1, this polynomial that we have obtained, this has a very fantastic property. What property? So we are actually trying to figure out the pole locations, right? Roots of this polynomial. Right, let me just copy the polynomial. Would be easier that way. So this was the polynomial, right? That we sought to figure out the root locations, right? Now this auxiliary polynomial has a fantastic property. We just figured out that s square plus 1 is an auxiliary polynomial. The fantastic property is that the auxiliary polynomial is a factor of the actual polynomial. So this is the polynomial which we wanted to figure out the solutions or the locations of the solutions. So the auxiliary polynomial is actually a factor of the original polynomial. So original polynomial was here third order polynomial, a fifth order polynomial. So now we have taken a second order factor out. So this is going to be a third order factor. So we are going to have some other part here. But the point being, this polynomial can be factorized this way. The auxiliary polynomial is a factor of the whole polynomial. This is not intuitively available. You cannot just come up with this from your mind, right? The auxiliary polynomial gives you that. So auxiliary polynomials are factors of the original polynomial. Just keep that in mind. So this is the auxiliary polynomial and this is the factor of the original polynomial. So now you have not only the, what should I say, not only the relative pole locations, but you can actually solve this equation because when you actually are solving this equation, maybe you are, imagine you are solving this equation. So if you're solving this equation, then you have a 0 in the right hand side. But if you know that s square plus 1 is an auxiliary polynomial of that, so which means s square plus 1 is a factor of this thing, which means this equation actually boils down to this. So I don't know what is there here, but I at least know that this is a factor of this. So which gives me at least two solutions right away. So I already know that the solutions of this are also the solutions of this. This is something we know from our childhood, right? So from this, we at least have two solutions right away. The solutions are from s square plus 1 equal to 0, which are s equal to plus minus 1j. Okay, so these are the two solutions already. So the auxiliary polynomial tells us directly that some of the solutions are directly available to you. You not only know the locations here, the relative locations, whether they are on the right half plane, whether they are on the left half plane, but you also have the solutions for some of them, right? Because the auxiliary polynomial is a factor of the actual polynomial. So that's the idea here. So the auxiliary polynomial is a factor of the original polynomial. So let me just write it down once again here. The aux poly is a factor of the original poly. So auxiliary polynomial is a factor of the original polynomial, and thus we actually know the exact pole locations if I wanted to. All right. So this row now has been discarded. So this has zeros. This row has been discarded. Now we have some information regarding the auxiliary polynomial. So there is one wonderful thing that we can actually divide this polynomial. We can actually divide this polynomial with this auxiliary polynomial and do a long division on polynomial. And then from that, we would have a reduced third order polynomial, right? So this is going to be a third order polynomial, right? So we can actually reduce this and construct a third order polynomial out of this here. And then we can do the Routh table on that. You see that we already know some of the pole locations, right? And we need to know the rest, need to know about the rest, the remaining three. So we can actually divide, do a long division on this. Okay, get the remaining polynomial, the third order polynomial left. Okay, and then from that we can actually figure out the relative pole locations for that. So now we have complete information about the 5 pole locations, right? 5 of the roots, all 5 of the roots. All right, so that is one of the ways in which you can approach this problem. There is another way in which you can construct the, rather reconstruct the new row. Okay, reconstruct this discarded row. Of course, this row gotten discarded, so that was discarded. So let's construct the new s to the power 1. Now, when you construct the new row out of when auxiliary polynomial is present, when an entire row has been discarded because the entire row became 0. So this is how you construct the new row. You take the auxiliary polynomial, differentiate it. Okay, the derivative of the auxiliary polynomial. Hold on. All right. So what you take the auxiliary polynomial and differentiate it. So let's differentiate it. And what you get 2s to the power 1 plus 0. All right, 2s to the power 1 plus 0. Right. So that is exactly what you put here. 2s to the power 1 and 0. That's how you construct the new row. So the new row is constructed using the derivative of the auxiliary polynomial. Okay. Again, don't ask me why these things happen. Just know that these things happen. Unfortunately, this is one of the most crucial things that you study in your control system theory classes here. But unfortunately, I cannot teach you the background of this. I cannot teach you how these things come to be, because this requires a lot of mathematics that is beyond undergraduate engineering, beyond any undergraduate engineering course. Way beyond that, in fact. So this new row is constructed through the derivative of this. So let me just take this. Maybe. So this new row is constructed the derivative of the auxiliary polynomial. All right, not a problem, I hope. Okay, and again we can do the reduction and forget this zero, doesn't matter really. Okay, so this row has been discarded completely now. Okay, now let's construct the s to the power 0 row. So when we construct the s to the power 0 row, what we have? We have 2 times 0 divided by 2, so that's 1. So that's the end of the Routh table. So we have successfully constructed the Routh table. We have discarded a few rows, but not a problem. So let's see the sign changes. So positive to positive, not a problem. 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 So we see that there are no sign changes in the first column of the Routh table. There are no sign changes in the first column of the Routh table, which indicates that there are no poles in the right half plane. So we see that there are no sign changes in the first column of the Routh table. Therefore, there are no pole on the right half plane. But that doesn't mean that all of the poles are on the left half plane. You understand what I'm saying? There are no sign changes in the first column of the Routh table. So that indicates that there are no poles in the right half plane. Not a problem. But that does not indicate that all the poles, so all 5 poles in this case, are on the left half plane. So that is not what it means. But that doesn't mean that all the poles are on the left half plane. That doesn't mean that all the poles are on the left half plane. Okay, so we know that there are no poles on the right half plane, but that doesn't mean that there are no poles on the left half plane, because or all poles on the left half plane, because you see that we constructed the auxiliary polynomial. We have a certain information, additional information. We knew that this polynomial had this factor, which indicated that when I wanted to solve this, ultimately our goal was to solve this equation. When I wanted to solve this, we would have a factor out like this, right? This would be a factor out, and these would be 2 of the solutions, which means these would be 2 of the poles. Okay, this would be 2 of the poles, right? So we see that since the auxiliary polynomial have roots at s equal to plus minus 1j. So s equal to plus 1j, s equal to minus 1j. So s equal to plus 1j and s equal to minus 1j. We know, so s equal to plus 1j, s equal to minus 1j. What are these? These are poles on the j omega axis. So this is plus 1j, this is minus 1j. So this is plus 1j, this is minus 1j. So this is sigma, this is j omega, and this is the s plane. We know that there are 2 poles on the j omega axis. So there are 2 poles on the j omega axis, and the remaining 3, it has 5 poles, the remaining 3 are on the left half plane. Okay, and here we have the remaining 3. The remaining 3 would be here. Remaining 3. Okay, the remaining 3 are on the left half plane. Got this? So this system had 5 poles. None of them are on the right half plane, but 2 of them are on the j omega axis, and the remaining 3 are on the left half plane. So the system is not exactly unstable, but also not exactly stable either, right? So the system is marginally stable. Since there are no poles on the right half plane, the system is not unstable. Since all of the poles are not on the left half plane, the system is not exactly stable. But since some of the poles are on the left half plane and some of them are on the j omega axis, the system is marginally stable. The system is marginally stable. Okay, the system is marginally stable. All right, so right, any confusion? You might have a lot of confusions. Okay, but we are going to solve a few more problems, and we are going to talk about the conditional stability, and then I believe the idea would be much clearer. Okay, but for the moment, let me give you one exercise problem that you probably would want to solve. It's a very simple problem. Let's try to solve this. You would try to solve this, I hope. Exercise problem. So let's say simple one. Let's take s cube plus 2s square plus s plus 2. Okay, that's the polynomial. Okay, try to construct the Routh table and solve this. Figure out how many poles are on the left half plane, how many poles are on the right half plane. There is something I need to show you. Okay, so let me just bring up Python here. All right, so we have brought up Python here, and just hold on once again. So we can actually call the numpy roots function and pass on the coefficients of the polynomial. Okay, so we can actually pass in the coefficients of the polynomial, and that would actually do, right? So let me just go back to this. So this was 148874. So coefficients in the order of descending power 14887. Okay, 148874. All right, so yeah, that is exactly what you need to write. And if you write it down, it actually gives me all the roots. Okay, it gives me all the roots. So you see that there is one on the left half plane, not a problem. There is another on the left half plane, not a problem. Okay, so this is one on another another one in the left half plane. Okay, not a problem. And these two are on the j omega axis. Now the problem is that these are being solved numerically. Okay, so let me just do options. Yeah, and that's nice. So these are the roots. You see that this is one of the poles that is on the left half plane because its real part is negative. Can you see this? I hope you can see this. Okay. All right. That's one of the poles that has has negative real part, so it's on the left half plane. This is another pole that has the negative real part, so it's once again on the left half plane. So this is the pole on the left half plane, but on the geometric in the real axis. Okay, it has 0 imaginary part, but these 3 are on the left half plane, and these 2 are on the geometric axis. Okay, so these 2 are 0 plus 1j, 0 minus 1j. So these 2 are on the geometric axis. But imagine you don't have this computer, you don't have this programs that can solve numerically. Under those scenarios, I mean, using the Routh is a godsend, right? Because this is really this would really help us. This really helped us back in the day, like 80 years ago, our ancestors, of course. 8 years ago, when the control engineers actually wanted to solve this sort of complicated problems, I mean, doing these numerical methods and solve the equations entirely was not an option. Okay, that's why people invented these things. Necessity is always the mother of inventions, right? So people wanted to have a technique that would actually tell us that would actually tell them the relative pole locations without actually solving for the polynomial. But here we partially solve the polynomial, you see. Okay, so we actually partially figured out that some of the poles would be here, and then we actually, through the computer program, we actually figured out that the other pole would be here and 2 would be here. 2 would be somewhere like here and here. So these are the 5 poles here. Okay. Oh, I have given my phone number earlier, so let me just write it down here. Okay, so you have my phone number. Just call me up at the end of the class. All right. So we have this information. Now let's do conditional stability. Let me get rid of the phone number. Okay. I hope you got this. All right. So let's talk about conditional stability. Now, usually what happens, so far what we are talking about absolute stability, which means that we're just saying whether a system is stable or not. It's just a binary answer, right? A system is stable or unstable. Now, when we discuss conditional stability, we discuss stability under a condition, right? So what happens is that sometimes a system is stable under certain conditions and the system is unstable under certain other conditions, right? So the system is stable under certain conditions, the system is unstable under some other conditions. So this is something what we sought to find out right now. Okay, so let's construct a closed loop system. Okay, so let's say we have a very simple system, say 1 divided by transfer function, like 1 divided by s plus 1, s plus 2, s plus 3. Now, can anybody tell me what is the advantage of having a system written like this? We right away know the pole locations. We right away know the pole locations as s equal to -1, s equal to -2, s equal to -3, and we right away know that the system is stable. Okay, so right away we know that the system is stable because we know the pole locations, because someone wrote this in the zero pole gain form, ZPK form, right? So that way we right away know the pole locations, and so we definitely know that the system is stable. Not a problem there, right? So we know about this. So this system is stable, not a problem. We don't have to construct any Routh table or whatsoever. But imagine this is a system, this is a plant, or this is a system that needs to be controlled. Okay, this is corresponding to a system that needs to be controlled. Okay, imagine something like that. Okay, this is a system that needs to be controlled. So that's the transfer function. All right, and maybe imagine the controller is a very simple controller. It's an amplifier. Okay, it's an amplifier with a proper gain K. Okay, it's an amplifier, just simple amplifier. Okay, and of course the signal actually goes to this one, not a problem. And of course there is a feedback, so the output that is coming out of this gets fed back to the comparator, So the comparator actually compares the desired value with whatever we have as the controlled output. Okay, so that's a comparator, and we are not assuming anything in the feedback loop because we are just considering it a unity feedback. So you are all aware of the nomenclature here. I am not going to explain the nomenclature anymore. And this is the comparator. So it's a plus, it's a minus. All right, so that's a comparator. It's a very simple unity negative feedback structure. Okay, now there is a k here, and this k is not, what should I say, it's not a fixed thing, it's a parameter. This gain k is a parameter. So something like, you all have seen this, right? So if you have some sort of a audio device, you have a potentiometer, right? That's a audio potentiometer or the volume potentiometer. If you just increase that, the gain increases, and subsequently you have a louder output. Okay, so this is sort of like that. So you probably have some sort of potentiometer, and there you have this gain accordingly, right? So this gain is actually changeable. This is a parameter, but this amplifier is actually a parametric one. Okay, so this k is a parameter. So parameter is sort of a variable that can independently change. It can independently change irrespective of what the value of s is. It doesn't matter. Okay, it can independently change. So this is a parameter. All right, so now we know that the open loop system is stable. So this is the system itself, right? We know GS itself is stable, but what about the closed loop system? So let's take the stability of the closed loop system. But in fact, in order to find out the stability of the closed loop system, we have to first calculate the closed loop transfer function. This is RS, this is CS, and the closed loop transfer function. What is the closed loop transfer function? In order to figure that out, you have to do the cascade operation here. Okay, that becomes K divided by S plus 1 times S plus 2 times S plus 3, and then we have a unity negative feedback. So I'm saying that the closed loop transfer function CLTF, that is defined by the Laplace transform of the output to that of the input, is GS divided by 1 plus GS HS, but in this case HS is equal to 1, so this is 1 plus GS here, but these two combined gives you the GS, right? These two combined, so that's necessarily K divided by S plus 1, S plus 2, S plus 3, and the same thing here, K divided by S plus 1, S plus 2, S plus 3. So we are trying to figure out, and of course times 1 because it's a unity feedback, right? So we are trying to figure out the stability of the closed loop system, not the open loop system. We know the open loop system is stable. Okay, so now if we do the simplification on this, we would have S plus 1 times S plus 2 times S plus 3 plus K, and in the numerator I would have K. All right, so let's simplify this a bit. Expand this. Let's, so that this becomes S cube plus just hold on, huh? This becomes (11). Oh, is it? Sorry, that becomes 6 S square plus 11s plus K plus 6. You can just do this calculation yourself. I hope I have done it correctly. Yeah. Correct. So that's the ultimate transfer function, the closed loop transfer function, right? So now we are trying to figure out the stability of this system. Now, of course, whenever we are trying to figure out the stability of any system, we take this denominator as polynomial, right? Now, there is just one more thing I need to mention here. This thing that we have in the denominator for this closed loop system is known with a special name. This thing, this polynomial that we have in the denominator for a closed loop system is known as the characteristic polynomial. because it tells you the behavior, right, in terms of stability at least. So this is called the characteristic polynomial. Okay, so that's the characteristic polynomial. Just keep that name in mind. I'm going to explain why it is called the characteristic polynomial. It has certain other implications as well. Okay, so we construct the Routh table out of this. So what is the polynomial we are dealing with? The polynomial that we are dealing with is S cube. It's a very simple third order. So 11s plus a plus 6. That's the polynomial. Now, I cannot just directly say, we cannot just randomly come here and say, okay, this satisfies the necessary condition for the Routh table, for the Routh service criteria, because there is a k here, and this k can have whatever value it wants. The k can have whatever value it wants, right? So it does satisfy the necessary condition only if this thing is also positive, because this coefficient is positive, this is positive, this is positive. Only if this is also positive, then only the necessary criteria is satisfied, right? So we have to first write down one condition under which the necessary criteria is satisfied, right? So let me just write it down. Condition under which the necessary criteria is satisfied is this condition: k must be greater than -6. If k is equal to -6, then we have a 0 here, and then 0, that poses a problem because that violates the necessary criteria, because that term will be missing. 0 means missing. And if k is less than -6, then this becomes a negative term. So we have positive term, positive term, positive term, then a negative term. Okay, that also violates the necessary criteria. So in order for the necessary criteria to be satisfied, k has to be greater than -6. That is in the condition. So we are now, by default, we are imposing conditions on this. Okay, so in order for the necessary criteria to satisfy, we need to have k greater than -6. All right. So now let's construct the Routh table to see whether there are more conditions that we need to satisfy. And let me be very frank here. This is one of those examples which you would encounter a lot. This is an example, a very particular example that you shall encounter quite a lot. Quite often you shall encounter this particular example. So please learn this example by heart. Okay, that's my request. Please learn this example by heart. Don't forget this example. Okay, so let's construct the Routh table. So I will start with S cube row, and then we would have the S square row. So in the S cube row, I have 1 and 11. So 1 and 11. 1 and 11. And in the square row, I have 6 and k plus 6. That's 6 and k plus 6. There are no reductions that we can do. There are no reductions that we can do here, right? So now let's construct s to the power 1 here. And then that's going to be 6 times 11, that's 66. Minus k plus 6 times 1, so that's k plus 6, like that. Okay, and divided by 6. Obviously, now, of course, that becomes 60 minus k divided by 6. 60 minus k divided by 6. That's the element here. Of course, here we have 0 here, not a problem. We have 0 here. And then the s to the power 0 row, that is actually this times this, okay, and minus this times this. And subsequently, what we see is that this is just divided by this, obviously. This is just k plus 6. You just calculate this. This times this minus this times this. So obviously this is 0. So this times this is this times this. And dividing by this actually gives you this. So it's a very simple thing. Right. So we have constructed the Routh table. We did not have any difficulty. Right? Or did we? We did not have any difficulty. Or did we? See very carefully. We said that k is greater than -6. So this is a positive quantity. not a problem. We assumed this in the necessary condition, and that is now helping us. So since we assumed k to be greater than 6 minus 6, this is a positive quantity. So this is a positive quantity, so not a problem. Always positive, right? Positive. All right. So we have a positive number, positive number, positive number. But what about this? When can this one be positive? Under what condition this is also positive? So see, in order for not to have any sign changes, this must also be positive. But under what condition is this also positive? Under what condition? So we see, if k is less than 60, then 60 minus k by 6 is positive, right? 60 minus k divided by 6 is positive. So they all have the same sign then, right? So if k is less than 60, then 60 minus k is positive, right? Right? 60 minus k divided by 6 is positive. So this entire thing is, all the entire row in the first column of the Routh table, the entire column of the entire first column of the Routh table are positive. So there are no sign changes. So these two conditions, when taken together, k must be less than 60 and k must be less than 6. So let me just write it down here. So this is positive. This is positive if k is greater than minus 6, and this one is positive. This one is positive if k is less than 60. You see, this term is positive if k is less than 60, and this term is positive if k is greater than 60. Sorry, greater than minus 6, I mean. Okay. So what we now mean to say is that in order for all of them to be positive, so there are no sign changes. In order for all of them to be positive, so that there are no sign changes, then these two conditions must be satisfied. These two conditions must be satisfied, right? So in order to not have any sign changes in the first column of the Routh table, so that all the poles are on the left half plane, right? Routh table. These two conditions must be satisfied. So k must be greater than minus 6 and k must be less than 60. So these two must be satisfied together. That is, k must be less than 60 but be greater than minus 6. So under this condition, the system is stable. So this is where we come up with conditional stability. We see that under this condition, the system is stable. Okay. So under this condition, the system is stable. Okay. As long as k varies between these values, or k has a value which is between these two values, the system is stable. Okay. Any confusion there? I hope it is very easy to understand, not a very difficult thing to understand. All right. So that is something we already have discussed, right? Not a problem. Now let's get back and copy the Routh table. Let's see what are the spectacular ways in which this can fail. What are the ways in which this can fail? See, if k is greater than 0, what happens? If k is greater than 60, if k is greater than 60, then this is negative. This is positive. If k is greater than 60, then this is definitely positive. But if k is greater than 60, then this is negative. Let me just write it down. Now let's say if k is greater than 60, then this this one is positive, this one is negative, definitely this one is negative. So this one is negative, but this one is positive because k is greater than 60. Okay, if k is greater than 60, then this one is negative, this one is positive. So let's talk about sign changes. So positive to negative, positive to negative, positive to negative, and again negative to positive. Okay, so positive to positive, positive to negative, negative to positive, right? If k is greater than 60. So we see that if k is greater than 60, then there are two sign changes. That is, two poles will be on the right half plane. Remaining one pole will be on the left half plane. One pole will be on the left half plane. So two poles are going to be on the right half plane, remaining one would be on the left half plane if k is greater than 60. So obviously the unstable situation. So this system is now unstable. Okay, if k is greater than 60, the system is unstable. Okay, what else can we say? What about k less than minus 6? If k is less than minus 6, let's say, if k is less than minus 6, so if k is less than minus 6, okay, in that case this is negative, then this is negative, this is no longer positive, this is now negative, but this is positive obviously. All right, because k is less than minus 6, not a problem. So this is a positive quantity. So we have positive to positive, positive to positive, but then a positive to negative. Right? So there is one sign change, positive to negative, right? You see, we are calculating, we are checking all these out without actually solving the equation, right? And solving the equation is very difficult here in this case because k is a parametric quantity. It can change its value, right? So now this is another situation. Let me just copy this and paste this in this. Just hold on. So what we are saying is that if k is less than minus 6, then there is one sign change, right? And that is one pole would be on the right half plane and remaining two poles would be on the left half plane, unstable nonetheless. And there is one more situation that is remaining here. There is one more situation that is remaining. So let me just copy paste the table once again to figure out the other situation. The one more situation, I mean. Okay, that one more situation is when k is equal to 60. When k is equal to 60. You see, there are no other situations where something else would happen. Okay, so you see, when k is equal to 60, if k is equal to 60, then this is a positive quantity. This is positive. But there is a problem here. If k is equal to 60, then this is a 0. So now if k is equal to 60, then this entire row becomes a row of zeros. See, there is a 0 here and there is a 0 here as well. So this entire row becomes a row of zeros. So if k is equal to 60, this becomes a row of zeros. So that's a difficulty 2 situation. Difficulty 2 situation. So if k is equal to 60, we encounter a difficulty 2 situation. All right. So let's handle that accordingly. So if k is equal to 60, let's now reconstruct the Routh table. Okay. So if k is equal to 60, then let's put the values, because it's an exact value, right? K equal to 60. So if putting k equal to 60, we get this. So if I put k equal to 60, then this becomes a 0. Then this becomes a 0. Then this becomes 66. This also becomes 66. Now, unfortunately, this will now have to be discarded because this is now going to be, this is now also going to be discarded because this is an entire row of zeros. So forget this entirely. Okay. And this row now has to be discarded, just like a difficulty 2 situation, right? So difficulty 2, discard the row. We are saying discard the row. So difficulty 2, discarded. So this is the discarded row. Okay, so this is the discarded row. Now this now gives me that auxiliary polynomial thing. This is now going to give me the auxiliary polynomial thing, right? So what we are saying is that this is now, okay, what is happening? Wow, the shape recognition is not working. All right, so this is the auxiliary polynomial. Auxiliary polynomial, and the corresponding auxiliary polynomial is auxiliary polynomial is 6s square plus 66, and we know that the roots of this auxiliary polynomial are also the roots of the actual polynomial. Okay, roots of this auxiliary polynomial are also the roots of the actual polynomial. So if I solve this, I also get the roots accordingly, right? So let's construct the let's solve this. So we know that whatever was the actual polynomial, the auxiliary polynomial is also a root of that. So in just other words, we can say, what was the equation? Equation was, so when I put k equal to 60 here, it becomes 66. So we see that this polynomial, what we had, what s cube plus 6s square plus 11s plus 66. So k plus, so we had k plus 6, but k is 60 in this one, so that's 66 equal to 0. We wanted to solve this equation, but this would be the same as solving this equation, 6s square plus 66 times something, a first order polynomial, okay, equal to 0. Now obviously that's going to be 6 times s square plus 11 times a first order polynomial equal to 0, because that's the auxiliary polynomial, and this can be cancelled out because very simply 6 is a constant number. Okay, and obviously we don't know exactly about this polynomial. We could actually know by solving this, by actually doing a long division. Okay, but let's not even bother about that, because that is not our intention here. So we know one of the solutions. So two of the solutions are, so two of the poles would be at where s square plus 11 is equal to 0. So that's a factor of this. So s is equal to plus minus j root 11. Okay, so j root 11. So essentially plus j root 11 minus j root 11. So that's the auxiliary polynomial, and that is from there we can actually construct the new s to the power 1 row. So the s to the power 1 row newly constructed would come from the derivative of the auxiliary polynomial. So if you differentiate the auxiliary polynomial, derivative would be 12 s plus 0. So that's going to be 12 and 0 here. Okay, and obviously this is now discarded completely. So now obviously if you calculate the s to the power 0 row, that becomes 12 times 66 minus 0 divided by 12, so that's 66. So we see there are no sign changes here. So there's a positive to positive, positive to positive, positive to positive. So there are no sign changes whatsoever. So there are no poles on the right half plane, but we already know that there are two poles on the j omega axis. So we understand that under this scenario, when k, therefore, when k is equal to 60, one pole would be on the left half plane and two poles would be on the j omega axis. And there is just one last scenario where you might say k is less than minus 6, k is equal to minus 6. In that case, this becomes 0. Then that is not a problem, because when this becomes 0, we assume it to be an epsilon. Okay, you assume it to be epsilon, so all of them are positive. Okay, so that is not a difficult situation to understand once again. So with all that, we have these scenarios. So we had this system, right? We had this system, and without actually ever looking at the locations, exact locations of the poles, we now have established these conditions for the system. We realized that when there are several possible scenarios, so we saw that when k is when k was between minus 6 and less than 60, okay, less than 60, between minus 6 and 60, then the system was stable. So 3 poles on left half plane and a stable system. The closed loop system was stable. So we are going to write closed loop stable system. Closed loop stable system. Okay. Then we saw that if k is greater than 60, then we realized that if k was greater than 60, then we realized that 2 poles on, so let me just write down 1 pole on left half plane, 2 poles on right half plane. Okay, that's exactly what we saw. So when k is greater than 60, then we saw, yeah, 2 poles will be on the right half plane. So this is something once again we derived. So it's a closed loop unstable system. The open loop system is stable, but the closed loop is unstable. Okay, then we had a particular situation where k was equal to 60, and we saw that 1 pole on the left half plane, 2 poles on the j omega axis. So closed loop system is, this is special ink, closed loop system, closed loop marginally stable. So it's a closed loop marginally stable system. Okay. And did we write down any other situation? Okay, equal to 60. Oh, k equal to less than minus 6, right? K less than minus 6, there is one sign change. And so if we say k is less than minus 6, then we would have 2 poles on the LHP. One pole on RHP. So unstable. And obviously, if k is equal to minus 6, we have a particular problem. If k is equal to minus 6, we see, just let me try to show it to you. Okay, yeah. So if k is exactly minus 6, then we have a particular problem. The problem is that this becomes the equation, right? So s cube plus 6s square plus 11s, right? So if k is equal to minus 6, just let me just write down. So the polynomial was s cube plus 6s square plus 11s plus k plus 6 equal to 0. But if k is equal to minus 6 exactly, then this becomes s cube plus 6s square plus 11s, that's equal to 0, right? So we have s times s square plus 6s plus 11 equal to 0. So this becomes a very weird situation. Here I have a pole not on the j omega axis exactly, but on the origin. Here we have a pole here. Okay, and the remaining 2 poles, you can actually calculate this. The remaining 2 poles would be here. Okay, so we see that this system is not exactly stable, not exactly unstable, not exactly marginally stable. This is a very special kind of system that is something we need to discuss in our future classes. So we are deliberately skipping that exact situation. Okay, and there is one more thing. Just one more thing before we end today's discussion. Please, once again, please ask any question that you might have. We are deliberately skipping the situation where k is equal to minus 6. What happens? We are deliberately skipping that situation because under that scenario, the system has a pole at the origin. Okay, at s equal to 0, right? Now, please tell me if you have any queries. There is just one more thing. Okay, a standard simplification. Okay, so if I have a first order system, it's a very simple thing to notice that if I have a first order system like s plus 5, you directly know the pole location, so not a problem. There is no Routh or Routh required. Okay, for second order systems, for second order systems, the necessary criteria is the sufficient criteria. Just keep this in mind. This is the observation. Okay, the observation is that, so for example, if I give you a second order system, okay, so whatever I have in the numerator does not matter. In the denominator, whatever I have in the numerator does not matter. In the denominator, let's say I have a second order system, so s square plus 20s plus 5. Question is, does it satisfy the necessary criteria? Does it satisfy the necessary criteria? If it satisfies the necessary criteria, it would imply that it also satisfies the sufficient criteria. So for second order systems, first order systems is trivial. For second order systems, if it satisfies the necessary criteria, then the system is stable. Okay, the problem becomes from third order system. Okay, so this is satisfying necessary criteria, stable, definitely. Okay, so let's say we have another example where I have something here, and this is s square plus 2. Does it satisfy the necessary criteria? No. So the sufficient criteria is also not satisfied. So this is not exactly stable. Okay, So you can actually figure out the exact pole location. So this is the marginally stable example. Okay, the poles are would be on the j omega axis. So necessary criteria is not satisfied. So let me just instead say, so necessary criteria is not satisfied. So it does not qualify as a stable system. It is not an unstable system. It is not to say that not being a stable system makes it an unstable system. There is something in between. Okay, this in this particular case, this is a marginally stable system. Okay, see an example. This does not satisfy the necessary criteria at all. Okay, because there is a sign change, okay, in one of the factors here, and thus this is not being satisfied. It is not satisfying the necessary criteria, and thus the system is unstable. Okay, this is unstable completely. So by looking at a second order system, you can actually tell directly whether the system is unstable or not. Okay, if any of the coefficient is missing, then it's probably not stable. Okay, if one of them have a different sign, two of them have different signs, then unstable, definitely. All right. So there are two exercise problems that you are going to get. And please ask any questions that you might have, please. All right, so there are a few problems that you are going to get for solving using Routh. So these are your exercise problems. So these are your assignment problems. Please note them down because you have to solve this. Okay, the polynomials. I'm just giving you the polynomials. You understand what to do, right? The question, to be exact, would be use the Routh criteria to check the stability of the LTI systems having the following characteristic polynomials. Okay, so number one would be this one. Okay, number two would be this system. Number two would be this condition. You have to now for the number two you have this question. So number one, this is the question. Okay, that will be fine. For number two, this is the question. So let me just write down GS and HS. So question number A. For that, GS is K divided by S times S plus 7 times S plus 11, and HS is equal to 1. So you understand this is a unity negative feedback system. Okay. So of course you have to check the closed loop stability. Okay, you have to consider the closed loop transfer function and take the characteristic polynomial out of that. Okay. All right, and the next one is GS is equal to K times S plus 20 divided by S times S plus 2 times S plus 3. And this is once again an unity negative feedback system. Okay. So these are the problems that you need to solve as your exercise problems. Okay, as your assignment problem. And this will be due next week. Okay, this will be due next week. So this will be due by next Wednesday. Due on 3/11/2021. Okay. So just keep this in mind. These are your assignment problems. Do you have any confusion? All right, so let's end our discussion at this point. Thank you for being here patiently for so long, and I will see you tomorrow. In the meantime, if you have any query, just you can get in touch with me directly via a phone call.